Hi everybody, welcome to this morning's seminar, which is a combination of in-person and Zoom. So we'll try and make sure that all the technology works okay. It took us about half an hour to get set up earlier. And today our speaker is Ryan Schoenbaum from the University of Melbourne, previously in California. He's been here for about a year and he's going to talk to us about conservation planning in northern Queensland.
Just get started? Okay, cool. Okay, can everyone hear me okay? Okay. All right, well, thanks for having me, everyone. And I'm excited to share my project on cross-realm conservation planning, and a big portion that's going to be bringing in climate change into the planning process. And we're going to be using the Burdekin region in North Queensland as a case study. And I also just love to acknowledge my wonderful advisory team between the University of Melbourne and James Cook University. Okay. And so just briefly kind of outline for what I'll be talking about. First, I'm going to go over what cross-realm planning is. What are some important gaps in prior approaches, why I chose the Burdekin specifically, and then because I'm about a year in, I'm not going to have any revolutionary results yet, but hopefully I just want to get across what the plan is and what our goals are. And so I can't really talk about cross-realm planning without first talking about systematic conservation planning. And so decision makers and land managers just want to know where they should invest their limited and valuable resources, and what kind of actions and where to place those actions. And so this is a kind of an overall framework that looks at kind of the domain you'll be working in, looking at the stakeholders who will be involved, and then going through a process of spatially prioritizing actions for example, conservation in the Great Barrier Reef Marine Park here on the left. And so they were able to successfully identify areas for different levels of protection. And so cross-realm planning is really just systematic conservation planning, but here we're trying to account for ways in which those realms are connected. So terrestrial, freshwater, and marine realms. And so why do we want to work with cross-realm planning? Mainly because the boundaries between those realms is in many ways imaginary. And threats originating in one realm often require actions to mitigate cross-system impacts. So thinking about runoff from catchments out into the Great Barrier Reef is a good example of that. And we also want to think about how maintaining ecosystem processes that transcend realms is important. So anadromous fish species here, and the delivery of materials and nutrients across realms. And then finally, management actions in one realm can also influence actions in the other. And so when you have a variety of objectives in a variety of realms, you start to get some interesting trade-offs emerging. And so this is how we typically think of these three realms: terrestrial, freshwater, and marine, which is kind of largely driven by jurisdictional boundaries of managing bodies. And so our research and efforts tend to be confined to these three realms. And so when we start to think through how are these realms connected, some first ones that come to mind are these more broad connections between realms. So we're thinking about floodplains or riparian areas around a river, and how that system is really connected beyond the channel of the river. And then thinking about the connections between freshwater and marine realms might be something like estuaries or mangroves, where we have species that can migrate between realms using that type of habitat. And so these tend to be kind of easily mappable features that are easy to target in a planning exercise. And next, a bit more of a constrained connection here, really commonly included in cross-realm planning, looks at how systems are connected through runoff from the terrestrial realm to the freshwater realm, and how those sediment and nutrients and contaminants from different land uses might flow through the freshwater system and then ultimately end up in the marine system. And so it's kind of difficult at times to really quantify this, especially the connection between freshwater and marine realm, where we're looking at kind of plume models in the ocean, and those models are getting better and better, and we're getting better at being able to try and capture that. And so a more diffuse connection type might be highly mobile species, such as amphibians or pelagic seabirds here. And while we're not trying to map out their exact flight patterns or things like that, it's possible to target where they're aggregating to ensure that those sites exist into the future. And so we also want to think about how we interact with realms, with each realm, and how that might modify the connections between realms. And so, for example, urbanization and agriculture might modify the catchment, which then modifies water flow and modifies pollutant delivery, which then washes into the freshwater systems, and then that moves out into the marine environment. Or we can think about it from another direction, which looks at how fishing pressure on marine species and populations might be reduced to a point where we're starting to see a loss of that delivery of upstream materials and nutrients if we're talking about an anadromous fish such as a salmon. And so this gets blown out. Point here I was trying to make is that it gets blown out until we get a figure like this with a lot of complex interactions, not only with how ecosystems are connected by biophysical processes, but how we interact with the landscape, how we modify the landscape, and then how that can also modify the connections and the transport of or the connections between ecosystems. And so there's a few ways that this has been addressed. This is just a figure showing a variety of kind of overviews of what realms are targeted and then how we're accounting for connections between them. I just highlighted A and B here because these are kind of two of the more commonly used approaches in this case. And so in A here, I'll bring up the cursor and highlight there's explicit consideration for actions in the marine realm or the freshwater realm, and we're planning in the marine realm in a way that avoids those land-based threats while kind of implicitly considering the terrestrial realm. And another way of going about this might be explicitly prioritizing actions in the terrestrial realm with implicit consideration for the marine realm in a way where we're trying to minimize the impact of those land-based threats. So we're trying to plan in the terrestrial realm in a way that minimizes the threat of runoff that is ending up onto the reefs. And more recently, I highlighted D over here because there's a bit more work going on recently in prioritizing both terrestrial and marine actions simultaneously, but also in a way where we're starting to see a mitigation of those threats flowing from the terrestrial to the marine realm. And so to walk through kind of a common way to quantify one of these types of connections, it typically involves a runoff model, in this case, a sediment runoff model, which is INVEST. And then we'll look at how that material flows through the freshwater system into the marine system, and then how that's dispersed into the marine environment. And then we'll translate that into some sort of quantifiable assessment of reef condition, and in this case, typically using things like benthic or fish indicator species that are associated with different metrics of water quality in the marine realm. And then we also want to kind of translate that to more socioeconomic values. And so we'll look at how that might affect fish populations, which are important for local fisheries. And then bringing that back into looking at scenarios in the terrestrial realm and how maybe different scenarios of land clearing might go back up and influence the export of sediment from land into the freshwater and into the marine realm, and looking at scenarios of how our fish populations might be doing in the future. And so ultimately we might end up with a figure like this one. This is out of Papua New Guinea, and this was a multi-realm simultaneous prioritization. So looking at both terrestrial, freshwater, and marine realms, and looking at conservation actions across those three realms simultaneously, while also looking at the connectivity of runoff from catchments into the marine realm, and trying to get a sense of where should we place our priorities to not only account for those connections, but to balance, to achieve objectives that we have on both on land and sea. And so this prioritization leads to some kind of highly nuanced, and you wouldn't give this to a manager and end up or to managers and be like, okay, manage all these areas. So it just kind of guides managers to look at areas and say, okay, we're going to draw circles around here and here, and we're going to work on managing those areas. And so a critical question still remains in cross-realm planning, which is how do we account for climate change? A really common approach is to include something called climate refugia. So just areas that we've identified prior to the prioritization approach that looks at regions that might be more resilient to climate change. And while there hasn't been much done in explicitly accounting for climate change yet, it's kind of for good reason, because it's really hard to know how species and ecosystems might change in the future. And then on top of that, how those connections that influence them might change too. And so that's why I chose the Burdekin, because it's a very data-rich region, which will be important for this. It's also a very highly modified catchment since European colonization, and that's led to some pretty significant water quality issues going on in the region, which then leads to the calls for the holistic management of the areas, and something called the Paddock to Reef Integrated Modeling and Monitoring Program, which reports on water quality in all the Great Barrier Reef catchments, but specifically I'm focusing on the Burdekin. And they also inform the Reef 2050 plan, which is a plan that has highlighted targets to be reached at the end of catchments by the year 2050. And on top of this, climate change remains a major threat, and how that'll influence those ridge to reef processes. And so just a little bit more context of the Burdekin region. Grazing is the dominant land use scenario, with about 90% of the catchment being comprised of grazing lands, which largely drives a lot of the sediment running off of paddocks into the freshwater and marine environment. And then sugarcane cultivation is largely responsible for a lot of the dissolved inorganic nitrogen that's reaching aquatic systems. And I also want to mention here that there is a bit of work going on in terms of how management actions at the paddock level might reduce those, reduce the amount of runoff. And so we're looking at how to kind of optimize actions here to achieve that. And so, yeah, because of this, and because of these, because of the runoff coming off these lands, the Burdekin of all the GBR basins has been highlighted as a priority basin. And there has been progress in recent decades, but especially with the Burdekin, looking at these the lower figures, even with modeled estimates given blanket minimum standards in both industries, we're still projected to fall short of what those end of catchment load reduction targets are. And so yeah, moving forward, we want to look at, okay, where should these cost-effective investments be made if we want to get to those water quality targets by those deadlines. And I just wanted to add this because bleaching events on the Great Barrier Reef are becoming more and more frequent, especially with back-to-back events recently in 2016 and 2017. And I just wanted to illustrate here that with climate change and bleaching becoming more and more frequent, if this pattern continues, then water quality becomes a more urgent, an urgent matter in the region. And so with that, a 2017 scientific consensus statement came out and said that climate change is the greatest threat to the GBR, but water quality will be what mediates its resilience. And that's led to those Reef 2050 water quality improvement targets in the water quality improvement plan. And yeah, so still there's that question of a cost-effective realization of this plan. And beyond that, we also might want to consider how ecosystem function and carbon sequestration in the region might be important objectives locally, as they are also important objectives globally too. And so given the exceptional modeling and monitoring in the region from a variety of institutions working throughout the Great Barrier Reef, this provides a good amount of data for all of these objectives. And so you might want to consider a few questions now that we know that there are sound, ecologically relevant water quality targets in the area. And so our question is, well, how do we get there first? And then there's also objectives beyond water quality across the land sea realms. So then we want to think about, what are some synergies and trade-offs when we try and bring in multiple objectives into a spatial prioritization approach across multiple realms. And then lastly, climate change is not explicitly considered in the Reef 2050 plan. So we also want to think about how climate change might impact getting to those targets and objectives. And so this is the framework I've landed on given all this. And so this is a multi-realm, multi-objective optimization, and we'll go through it, but starting off in the catchment, in the terrestrial realm here with objectives of runoff and biodiversity and carbon. And then moving into the marine realm, we'll be looking at something called the Allen Coral Atlas, which I'll get into, but essentially a distribution of the Great Barrier Reef, as well as a variety of other objectives in the marine realm that are put into a spatial optimization framework, where we define the targets, how much of a species we want to try and protect or habitat we want to preserve, the cost of action, so the cost to reserve a piece of land or to improve a management practice in the region, or defining constraints such as what the end of catchment load reduction targets for sediment might be, and then having some sort of way of delineating connectivity across and within realms. And ultimately, going back to that Papua New Guinea figure here, you might expect something like this in the Burdekin. And it's also common to use a software called Marksan, which is a spatial prioritization software, which kind of assesses where things are across the landscape, what are your targets, what are your actions, and what's kind of the most cost-effective way of achieving those. However, here we're going to be working with something called integer linear programming, which is in many ways functionally similar to Marksan, except it gives us a bit more flexibility in how we define the problem specifically, and also in how we can maybe define types of connectivity spatially. And lastly, we want to do this for 4 climate change scenarios out to the year 2050. And so objectives will be assessed based off those CMIP6 climate change projections. And this is just my thesis structure with 4 aims. So each aim will represent a chapter of my thesis, with aim 1 being more of that catchment centric approach given the current scenario today. And then that moves into aim 2, which will look at how climate change affects those objectives. And so here we're kind of to go back to that to those kind of overall approaches of cross-realm planning. At this point, we're kind of at that. What would that be? That'd be the B. I think it is the B in the figure, where we're setting explicit targets in the terrestrial realm, while kind of implicitly considering the marine realm by setting those runoff targets for runoff. And then aim 3 is a tangential aim to the rest of the aims, and it's kind of a standalone risk assessment for sea level rise in the Burdekin region, and we'll be looking at mitigating risks of sea level rise to coastal sugarcane growers in the lower delta region, and priority areas to reserve or restore to mitigate that risk. And that all finally feeds into aim 4, where you have that multi-objective cross-realm planning exercise, where we tie in the marine features. And so here's the Burdekin and all of its sub-catchments. For the planning units we'll be using in the terrestrial realm, we'll be working with the sub-catchments that are in something called the source GBR runoff model. That's part of the Paddock's Reef program. It's how they model the runoff that reaches the end of the catchment. And so we'll be working with that spatial unit of about a few 100 square kilometers, which will have a value for sediment or dissolved inorganic nitrogen, or the content of a certain species, or carbon or something like that. And then for the coastal and marine realm, we'll be looking at using commonly applied hexagonal planning units, and then also looking at possibly along the coastline here, where a finer scale planning unit might facilitate the ability to account for that a rapid change over a small distance in a coastal area. And so just to walk through some of the data streams I've identified so far for each aim and how they kind of fit together. First, in aim 1, there's the load reductions that are associated with management practices from the source modeling efforts, which is an existing data set. There's also been a lot of work done already looking at the cost to mitigate loads in dollars per kilogram per hectare. It's phenomenal because it's easy to put into to an equation. And then we also have those end of catchment load targets to meet. And so this is just an example of the amount of sediment that is coming off of each subcatchment and how much of that sediment is contributing to those end of load targets. And so you can see there's areas, kind of hotspot areas in the Burdekin, especially for gully erosion. And this is in the, I think the triple B catchment, as they call it, the Bowen Broken Bogey catchments. And for species data, we'll be working with NEST's threatened species data. There's about 1,400 species of conservation concerned in that data set. However, all of them are not in the Burdekin, but a good amount of them are. And we'll also be looking at coarse ecosystems and habitats such as corridors. And so this figure on the right just highlights really biodiverse areas in the Burdekin, but also corridor habitats that we can target to make sure that those corridors exist into the future. And this map on the left of all of Australia is just an example from that NESP data set. And this is the ghost bat, just to illustrate the spatial extent and resolution we'll be working with. And then finally, carbon flux will be assessed through land use and land cover and possibly a few actions as well. Carbon data is available through NQ Dry Tropics, which is just the regional management body in the area. And we'll also have some action, or sorry, a carbon value associated with some of the actions. So for example, if you clear a bunch of forests, there's obviously a loss of carbon from that action. And so just an example of the data sets available through NQ Dry Tropics. And one of them is carbon capture. So if we want to set targets for the amount of carbon that we want to maintain capturing, that data exists already. And this is kind of the bigger, one of the bigger aims in which we've been working on a lot recently. And we just had a workshop up in Townsville looking at how to embed climate change projections into the paddock to reef team's models. And once we do that, then we can work on assessing the efficacy of management actions out to the year 2050 and our ability to reach those water quality targets. Next, CMIP6 species distribution data has already been done as well. I'll get into that right after the slide. But something that's still being worked out on our end is how kind of coarse features and possibly carbon might change into the future under different climate scenarios. So we still have a bit to work out there. So yeah, like I said, Dr. Carla Archibald out of Deakin University has already been working on a lot of CMIP6 projections for species distributions. And so we'll be bringing that into the framework. And then this figure on the bottom here just kind of goes through the process of what it means to embed climate change projections into a catchment model. And so what we need to do here is the global catchment models are a very coarse resolution. And so we need to downscale that to something that's compatible with a runoff model in the region. And so we'll downscale that using precipitation and evapotranspiration data from the GCMs and from historical data sets, which then we can finally plug into the models with a few other considerations that I won't get into here, but ultimately it allows us to assess how runoff changes into the future and then how loads in that runoff change into the future. And then the third aim, looking at sea level rise, we're going to be coupling two models here. One is the sea level rise affecting marshes model, and the other is the Invest Coastal Vulnerability Assessment model. And here we'll be prioritizing actions of reservation reservation or restoration to mitigate risk to coastal growers. And hopefully we can look at a few trade-offs or potential win-wins through sea level rise buffering and ecological value. And so the Invest tool, this final box here, it typically works by looking at a binary scenario of coastal ecosystems in place or absent, and then how does risk change into the future based off scenarios of sea level rise. And so we would end up with a map like this, where we have kind of risk indices along the coastline based off your risk to sea level rise in the future if you lost your ecosystems for whatever reason. And so the change here that we want to work on is using sea level rise affecting marshes model to take where we know coastal ecosystems are now and model how they might look in the future, and then run them through the Invest Coastal Vulnerability model to see how risks might change in the future under those specific scenarios of sea level rise. And so finally, that brings us to aim 4, where we bring in elements from those aim 2 and aim 3, where climate change is introduced. And then we're going to bring in the marine features, marine features and targets and threats. And the biggest data sets we're going to be using in the marine realm is something from, it's called the Allen Coral Atlas, which is a much more high resolution data set now of the Great Barrier Reef, which was derived through satellite imagery. Pretty amazing stuff, in my opinion. And it gives us a bit more nuance when we start looking at how we're setting targets across the Great Barrier Reef for protection, things like that. And so we can base this now off of either benthic cover classes or even coral types in certain areas. Additionally, we will be working with NEST's seagrass distribution data set. And once we have, so now we can set targets for mangroves, we can set targets for seagrass, and we can also set targets for the Great Barrier Reef area. And by doing that, we're kind of implicitly capturing connectivity between those ecosystems in the marine realm. Another way we might capture connectivity is through targeting nesting or aggregation sites for some sea turtles or seabirds. And there's also a pretty good data set that's assessed where sources of larvae are strongest throughout the Great Barrier Reef and for seagrass as well. And so that could be another data set we could bring in. And so finally, we get to a really challenging part of the project, which is looking at cumulative threats in the marine realm. Fortunately, there's already been some work done on this from Wolf and colleagues in 2017 that looked at cumulative threats in future scenarios of climate change. And something we might be able to tweak here is how that nutrient runoff factor changes given the modeling work we're doing with the catchment models. And so finally, that gets us to the end here, where we have a multi-realm, multi-objective optimization of a variety of actions under 4 different scenarios of climate change. And yeah, so now we can assess is there any disparities, is there any overlaps, how do things change under those different scenarios, and how does that inform management based off those climate change projections. And so finally, some questions to explore might be, where and what are the synergies and trade-offs when comparing when compared to a catchment-centric approach? How do actions in the marine realm compare to the current marine park design? And then an important one is, how do costs compare to current investment programs? And then finally, how does climate change impact the ability for us to reach those targets compared to the current scenario? And so lastly, outcomes, we expect to address gaps in prior approaches by explicitly accounting for climate change in that sea level rise too. It'll be multi-objective in nature with targets across multiple realms. And then we also want to bring in something novel here, which is integer linear programming, which is becoming more common in conservation planning in general, but yet to see it for cross-realm planning. And then we also hope to build the capacity for collaborations across institutions, agencies, and a variety of stakeholder groups, which then we hope to distill concepts from this project in the GBR for hopefully some global applications. And so with that, I'd like to say thanks for your time, thanks for coming, and thanks for having me.